The geometry of this parabolic dish is a deliberate engineering choice. Every structural rib is positioned to intercept complex vector fields from the deep cosmos. To understand exactly what this telescope is catching, we define the electromagnetic wave as a periodic disturbance traveling through space-time. It exists as the continuous interplay between an electric field and a magnetic field. Acoustic waves require the mechanical compression of a gas or a solid to travel. By contrast, electromagnetic waves rely entirely upon the vacuum's own fundamental constants, the electric permittivity and magnetic permeability of free space. Explaining how a wave propagates without a physical medium forced Michael Faraday and later James Clerk Maxwell to move beyond the study of localized charges and map the behavior of invisible, continuous fields. The engineering of all modern wireless systems depends on the specific geometric lock that exists between these electric and magnetic fields across space and time. The massive steel lattice of this telescope dish serves as a physical interface designed to align with the orientation of these arriving fields. The electric and magnetic fields drive one another in a self-sustaining engine of mutual induction. Faraday's law in differential form shows that when a magnetic field changes over time, it generates a spatially curling electric field wrapped around it. Ampere's law provides the symmetry that changing electric field, specifically the displacement current, generates a spatially curling magnetic field. This continuous mathematical handshake pushes the fields forward. They decouple from their original source and propagate through the vacuum at the speed of light. Without these specific relationships between spatial curl and time derivatives, the electromagnetic energy would permanently stay localized to the source charges. The vacuum acts as a reactive medium that supports this continuous, self-sustaining vector interchange. To trace the origin of these fields, we look at the short current element, or dipole. A vertical radio tower operates on this principle. Inside that tower, a transmitter drives a time-varying current, oscillating rapidly up and down the z-axis. Close to the antenna, in a region called the near field, the resulting electromagnetics are chaotic. The math is dominated by complex terms that drop off proportional to the inverse square and inverse cube of the distance. In this 3D plot of the near field, the electric and magnetic vectors are 90 degrees out of phase in time. When the electric field hits its maximum strength, the magnetic field is at zero. Because they oscillate out of sync, they generate reactive power. The energy sloshes back and forth between the physical antenna and the immediate surrounding space. Energy trapped in this reactive state cannot carry information far. It stays anchored to the source. The near field acts as an electromagnetic reservoir. It dictates the physical design of the antenna itself, but it does not contribute to deep space propagation. As distance from the antenna increases, the geometry of the field simplifies. We enter the far field. We map this transition by taking the complex mathematical curl of Faraday's law and substituting Ampere's law into the result. This yields the Helmholtz wave equation. It proves that the spatial curvature of the electric field is tied directly to its acceleration in time. At extreme distances from the source, the expanding spherical wavefronts become so massive that they appear locally flat. We refer to these as uniform plane waves. In this limit, the complex reactive components vanish. The only surviving mathematics are the radiation terms, which decay at a rate of 1 over the distance. The locked geometry of the far field is the stable structure that remains once the turbulent influences of the source antenna drop away. In the far field, the uniform plane wave is strictly transverse electromagnetic. Look closely at this animation. The electric field on the x-axis and the magnetic field on the y-axis are now perfectly in phase in time. They peak and hit zero simultaneously while remaining rigidly orthogonal to each other. The magnitude of these two vectors is fixed by intrinsic impedance, calculated by dividing the vacuum's magnetic permeability by its electric permittivity and taking the square root. For any wave traveling through free space, the ratio of the electric field to the magnetic field is always approximately 377 ohms. This ratio is a fundamental constant of the vacuum. It remains the same regardless of the transmitter's power or the specific shape of the antenna. The vacuum provides a structural template, and every wave propagating through it follows this rigid geometry. Because the fields are now perfectly aligned in time, they transport real, physical energy. This animation illustrates the pointing vector. By taking the cross product of the electric and magnetic fields, we generate a third vector representing the directional power flux density. Because far-field vectors peak together, their mathematical product is always positive. The energy flows continuously outward. When this power flux finally arrives at the parabolic dish of a telescope, the time-varying magnetic fields induce a voltage in the receiver, reversing the same induction process that launched the wave. We can only extract that voltage and read the data because the fields arrived perfectly locked and orthogonal. The rigid geometric handshake between two invisible fields is the mechanism that allows physical force to cross the universe and connect us to the stars.